surface, as we've already seen, has a plethora. That means lots of different kinds of features. You can see all kinds of features that indicate historical water runoff, but absolutely no evidence for liquid water on the surface right now. No water, no rivers, no oceans, nothing like that. Also evidence for historical massive amounts of volcanic activity, like Olympus Mons here. Such a tall volcano, it actually extends beyond the frost layer on Mars. The base of this volcano would basically cover most of Texas. It's such a huge volcano, much bigger than anything you see on Earth. And we also see canyons and dunes. All right, so as I mentioned before, there's evidence for this lava flow that probably occurred around 3 billion years ago, probably around the same time that the moon was actually experiencing lava flows too. But we think that right after that volcanic period, the planet essentially started to cool off so rapidly that the internal heat was kind of quenched by cooling, and we lost the convection that you have to have if you want plate tectonics. If you want to get plates to move around on the surface, you've got to have that internal convection, because the plates are riding on the surface of the convective cells. So because of the rapid cooling, there's little plate tectonic activity, but there is evidence for a brief period of tectonic activity. And in fact, the best evidence for that is this funny-looking chasm that I pointed out to you before, which I said is kind of like a super version of the Grand Canyon. It's probably about 100 times larger than the Grand Canyon. And what we're seeing here is not a water erosion feature. So it's much larger than the Grand Canyon, and not even formed in the same way, because no river ever ran through that. They could make a movie called A River Doesn't Run Through It. Have you ever heard that? The river? Yeah, that works. A river doesn't run through it. Never did, as far as we know. But what we think happened was that during the early period of time when Mars actually was still molten in the interior, there was an initial attempt for convection to actually create tectonic motion. And the Tharsis region right here, well, the Tharsis bulge through the equator there, is actually the initial attempt of convection to create an upwelling, like it's trying to create a process there. But it's fizzled out because of cooling. So what we basically have is a region where it started to bulge up, and it bulged up so much that it actually created a tectonic fracture. It just started cracking apart. So when we look at this Mariner Valley, it's called, what we're actually seeing is a tectonic fracture on this Tharsis bulge, which is a pretty significant elevation, 10 kilometers, a few billion years ago. So this is, again, focusing on this Mariner Valley, we call it. Connected with Tharsis is also these volcanoes I'm talking about. So when this Tharsis bulge activity was going on, that was also the same period of time when these giant volcanoes were active. So we had a period of volcanic activity coupled with a kind of abortive plate tectonic phase, which both fizzled out around the same time, a few billion years ago. And so this is just a topological map looking at Olympus Mons and a few of these other volcanoes that are not active anymore, but were going crazy a few billion years ago. All right, so I already mentioned before the reddish color is basically due to the presence of iron on the surface and iron oxide. There's enough oxygen in the atmosphere to lead to oxidization. Because of the rapid cooling, we think there was very little differentiation. So whatever iron there is, and remember, there's really not that much iron on Mars. We know that because the average density is only 3.9 grams per cubic centimeter. But even with a density that low, we're not saying there's no iron. We're just saying there's not nearly as much as there is on Earth. But what is there is pretty much distributed through the whole planet because it's solidified before differentiation could actually be completed. And we think that's partly because Mars is a small planet, and small things tend to cool faster than large things. You may have noticed that little small birds need to eat a lot more than larger birds. They need to eat constantly because small birds actually have a large ratio of their surface area to their volume. And their volume is where their organs are generating metabolic processes of heat, right? But when you're a small bird, you have a very large ratio of surface area compared to your volume. So you have to constantly eat to generate heat to balance what's being lost from the surface of your body. Large birds have a smaller amount of surface area for their volume, so they just were able to keep their heat better. So if you think of it that way, Mars is kind of like a small bird. Now it didn't have the energy source to replenish itself, so instead it just cooled off. It just cooled off faster, it was smaller. And with the absence of a lot of heavier radioactive isotopes, which tend to be clustered near the sun, which is actually, again, that's differentiation, because radioactive material is more dense, tended to be closer to the sun. So Mars didn't even get much of the radioactive stuff, and so the radioactive decay was not a source of continued heating for Mars. So it kind of lost on 2 counts. The small planet, well, 3 counts, I guess. The small planet, it's far from the sun, so it didn't even have much solar heating, and it didn't have much radioactive decay either. So again, bottom line is it cooled off too quickly to differentiate completely. So its interior is probably a bit on the homogeneous side compared to what we've seen for the other terrestrial planets. Okay, surface of Mars, and this is one planet where direct observations revealed that the sidereal day, the sidereal rotation period, is about 24.6 hours. And this was actually known for a long, long time because you don't have to play guessing games with Mars. There's really enough features on the surface of Mars that even with early telescopes, you actually could see features coming back around on Mars' surface. So it wasn't like Mercury and Venus where people were just imagining things. You actually see enough there that we know that the rotation period is very similar to Earth's rotation period. And the rotation axis is also very similar to Earth's rotation axis tilt, about the same tilt. So if it weren't for the fact that Mars is only about half the size of Earth, in this sense, in terms of the spin and the tilt of the axis, it's the nearest twin that we have to Earth in the solar system. Okay, so we'll just say go a little bit farther here. So the highlands and lowlands, I already mentioned that when we look at the topographical maps, we find that the southern hemisphere of Mars has a much higher average elevation by several kilometers than the northern elevation, the northern hemisphere of Mars. And actually just that even, just the higher elevation in the southern hemisphere, that also could be due to this abortive phase of tectonic activity, where the whole southern hemisphere was kind of hotter than the northern hemisphere, and that was starting a convective process, which just fizzled out. So the altitude contrast that we see between north and south could actually also be due to that short-lived phase of tectonic uplifting. Now, if we look at the ages, we see something which reminds us a little bit of the moon, because we see that the highlands in the south are about 4 billion years old, and the lowlands in the north, which turn out to be lava-filled, are about 3 billion years old. Very similar to what we saw when we looked at the highlands versus the Mare on the moon. So we're kind of seeing something similar here, but the only difference is that what we would think of as the Mare on Mars, they're actually segregated to a separate hemisphere, the northern hemisphere, whereas on the moon, the Mare and the highlands are kind of mixed together. Okay, so I guess I'll just end here for today, but I already kind of covered this in words. This is that upwelling that occurred around 3 billion years ago or so, when the Tharsis bulge actually was able to start forming. And this is what we think fizzled out and left us with the geologically inactive planet that we see now. So we'll finish this on Thursday, or Tuesday, today's Thursday. And let me see, the next exam is 2 weeks from today.